Welcome to Winchester Cafe Sci Online, and a special welcome to those joining us for the first time. If you enjoyed tonight's talk and you're not on our mailing list, you can sign up for it at our website, wincafesci.org.uk, to be notified about future talks. Tonight's speaker has a PhD in satellite imaging and complex systems simulation from the University of Southampton, during which he developed a new method for monitoring air quality from high-resolution satellite images. After completing his PhD, he worked as an academic for a number of years on projects including extending his PhD work and monitoring population movement after disasters from mobile phone data. He's now a freelancer in geographic data analysis and related software development, currently working with clients including Anglo American, Satellogic, and the Royal Navy. He has a wide range of interests and expertise alongside his professional area of specialism, including UK railways, particularly their signalling systems, nuclear power, and space missions. Please welcome Dr. Robin Wilson.
Right, hello everybody. As William said, I'm Robin Wilson, and I'm going to talk about railway signalling in the UK, with a particular focus on learning from accidents that happen and how that's helped railway signalling develop over the years. So just to start off, really, the first thing to point out is that this is what the inside of a train cab looks like. You'll notice there's no steering wheel. Trains run on rails, as most of you probably know, and so one of the jobs of the signaller, as well as making sure that trains are safe, make sure they go the way they want to go. The driver has no way of controlling which direction the train goes in. Start and stop. You can't go left or turn right. And the way this works is by points on the track. They look like this. They've got a movable blade in them, and that lets you see the blades moving. This image here, it lets the train go either to the right or straight ahead. In this example, that's one of the things that signallers do. They get trains to the right place. But the other thing they do, which is something a lot more important, is get them there safely. Now, back in the very early days of railways, your railways were first developed in the 1800s, they didn't really have signallers, because they didn't really need them. If you haven't got many trains going around, then you're unlikely to have them crashing into each other. And in terms of getting to the right place, if you want to go a different route on a set of points, you can stop your train, get out of the cab, pull the lever, get back into the cab and start your train again, and off you go in the way you want to go. So dear. We are having significant issues, aren't we? That's not good. Let's sorry about this, everyone. Let's see. Oh, so that's working. Let's try this again. That seems to be working. The first intercity passenger railway was the Liverpool and Manchester Railway, which opened in 1830. And on that railway, they had what they called policemen, who were responsible for two things: signalling and the security of the trains and the track and getting rid of unwanted people and so on. And they were spaced every mile along the track, and they gave signals to the trains. And initially, those were just arm signals. They then had red-green flags, and they used those simple levers that I just showed you to move the points and get the train going in the direction it needed to go in. Interestingly, this is why signalmen still are known as hobbies by some people, because it comes from the original job as a policeman. And then they developed a bit more into having some fixed signals of some sort. So these were the sort of fixed signals they had. Were early forms of what we call semaphore signals. They had an arm sticking out that moved in different positions, say different things. So sticking out horizontally was danger, stop, down at an angle was caution, and then hidden inside the post. So with that arm hiding down inside the post it was stood on, was all clear. It's safe for the train continue. And this is the kind of thing they look like. Originally, they were just poles by the railway side with a bloke sitting by there, not even with any shelter or anything. Later, they developed early forms of signal boxes where they had a bit of shelter for the man and some levers he could pull wires that went up these poles and move the signals into the right place. So now we're going to look at our first railway accident that led to improvements in signalling. And I could have chosen any from hundreds of accidents at this time. Railways were really not a very safe place. In fact, someone died on the very first day of opening the Liverpool Manchester Railway. But that was mostly his fault because he stepped in half the train. Anyway, this was Abbots Ripton in East Anglia, killed 13 people, injured quite a lot more. And the reason for this was it was cold weather and the signals froze at their proceed indication. And you remember, proceed was hidden inside the post. They were using the absence of some kind of signal as a thing to say it's fine to go, which is not really a great way to do it. You want to have presence of something meaning it's okay to go. They did various changes. They moved to different sorts of semaphores that didn't hide inside the posts when they were proceed. And they also decided to keep all signals at danger until they had to be cleared. And that's something that still happens deeply. The vast majority of signals on the railway network will be red all of the time, apart from when they need something other than red for a train to go past them. And by default, it's safe all the time. And they also did lots of other things, and most of these accidents had a lot of impact on things that weren't signalling. So in this case, they improved the rates. In various other accidents, they improved the quality of the carriages or that kind of stuff. But we won't focus so much on that tonight. The key question really is, you have these bodies spaced along the track, but how did they know whether to say go or stop the train? Well, they did it on what was called time interval work. If it was less than 10 minutes since the train had gone past, they'd stop the next train. If it was a bit over 10 minutes, they'd say, okay, go ahead, but go slowly, at caution. And if it was more than 17 minutes since the last train passed, then go ahead at full speed. That works fine until a train breaks down somewhere on the track, and then the fact that you're 17 minutes behind, it doesn't matter because that train is stopped and you go straight into backwards, particularly if that's around a blind curve or something. So this is not fail-safe. You are assuming that everything will be okay 20 minutes after the train has gone by, which is not necessarily the situation. And to make this better, we really needed a new form of communication between these signal boxes. Remember, this was the 1800s, we didn't have telephones or the internet or anything like that. We did have the introduction of the electric telegraph, which used electromagnetism to send pulses down a wire, and you could send messages either by the pulses being a bell, or even with this thing shown here, by using the little needle here to point to different letters. And it was very famous at the time because it was used to capture murderers. Police in London sent a message with telegraph down the line from Paddington Station saying the murderer has got into the third carriage of the 1730 train, and then they stopped it at Slough and the police went into the third carriage and arrested the man. So it was quite an exciting new technology. And they realised they could put this communication method between signal boxes. So here you've got a number of signal boxes along the bottom, 1, 2, 3, 4, a couple of trains. And at the moment, this signal box is displaying a red signal saying you mustn't go past. But as soon as that train gets past the next signal box now knows that this section between signal boxes is empty of trains, because the train that's been sent through has gone past him. So he sends a message back to the signal box before him saying, train has gone out of my section now, it's clear, you can send another one in. And then that signal moment changes his signals to green and lets the next signal, the next train into that section. This method of communicating between signal boxes is absolutely key to what's called the absolute block method of signaling. These bits between signal boxes, these gaps of track between the signal boxes are known as block sections. And signal boxes would send messages to each other using the telegraph saying, I've got a train here, can you accept it? And the next signal box will go, oh no, I can't accept it at the moment, there's another train in that section. And then when that train's gone, they'll send a message back going, right, the train's gone out of the section now, I can now accept your next train. So the absolute rule of absolute block signaling, if I can put it like that, is that there is absolutely only one train in each block section each time. That still applies today in areas of absolute block signaling. They also developed the sort of signals that were used at the time, and developed into two types: distant signals and stop or home signals. That's because trains take a long time to slow down. They haven't got tyres on a road like cars, they've got steel wheels on steel track. They don't have very good braking characteristics, so they have to be warned when they need to stop. So a distant signal is put a bit of a way before the signal that's telling the train to stop, and it warns him, slow down now, because when you get to the next signal, you'll be expected to stop. In this case, distant signals were yellow, and they still are. Stop and home signals were red. In these days, there were lots of different railway companies operating across the country, and they couldn't agree on how to make their signals read in the same way. So you have upper quadrant and lower quadrant signals. Luckily, they all agreed that straight out means stop, which is really useful that they agreed that, thank goodness. But some railway companies had signals facing downwards for go, and some railway companies had signals facing upwards for go. This was also the time of building proper signal boxes. These were signal boxes that were located a little bit. These are the sort of traditional signal boxes that started to be built around this time. They had typically a sort of brick or wooden bit at the bottom, with all the sort of mechanisms for the interlocking, which we'll cover shortly. And then at the top, they had an area for the signalman to stand and operate the signals. And this was done using a frame of levers. This was the point at which they started to move multiple signals into one signal box, and you get this traditional looking signal box, various different styles here, with a brick bit at the bottom which contains some of the mechanisms, which we'll cover later on, and then a bit at the top with lots of windows for the signalman to see what's going on, and then a frame full of levers to control the signals. Now, here we were controlling signals that weren't just directly above the signal box, but maybe a slight distance from the box, and they were controlling different sorts of signals and points. And the levers were color-coded to show what sort of thing they controlled. So here you've got red levers for stop signals, yellow levers for distant signals, black for points, blue for something called point locks, which make sure that the points stay in the position they're in. The train is going over them, which is very important, or you might derail the train, and then white for any spare levers. And these signal boxes could get pretty massive because you needed one lever for every individual bit of equipment that you controlled. So this is part of the track diagram of Yarmouth South Town signal box, Yarmouth in East Anglia. And if we zoom in, you can see all these numbers on the diagram. These are all individual things that will be controlled by the signal box, and will all have their own lever. That's their lever number. You can see you've got signals here, you've got points here, you'll have facing point locks there, either end of the different points. There are lots and lots of different things controlled by the signal box, all of which would have to be controlled by a lever, which had to be pulled in the right sequence with all the other levers to do what you wanted. As I said, signals and other apparatus could be controlled at a certain distance from the signal box, but not too far. So you could control signals up to a mile away, because the signal was fairly easy to move with a lever attached to a wire that went through pulleys. You can see kind of here all the wires going out of the bottom of the signal box there. But it was only 350 yards away that you could control points, because points needed to go in both directions. They had rods that were linked together in complicated ways. And actually some points that were far away from the signal box were very difficult for the signalman to pull. They'd have to really brace themselves against the frame and pull the lever with all their might. And this meant you had lots and lots of signal boxes, because anywhere you had points, if it was more than 350 yards away from some other points, you'd have a whole new signal box just for those points. So this is a map of the area around Didcot, just south of Oxford. And these are all the signal boxes that there were. So this is 5 miles of track along here, with a little bit more track going up here at the junction. And you see you had 7 signal boxes spread along these 5 miles of track, because there were points down here for a crossover, there were points here around the station and the junction, there were more points here, and they all had to be controlled by their own signal box just for the points in that particular area. Another key thing about signalling in these days was the introduction of mechanical interlocking. This was a sort of mechanical computer that was connected to all of the levers and stopped you doing dangerous things. So, for example, it wouldn't let you set two conflicting routes, because the bits of metal that you can see here, which have got notches in them, would all move against each other and physically stop you pulling the lever. So if you've cleared the signal in one direction, it will physically stop you pulling the lever to clear the signal in the opposite direction at the same time, until you put that signal back, and then you can do this. There are other things as well. So you must have to put the distant signal to caution to warn the train to stop before you can pull the lever to set the main stop signal to stop. So you always have that distant warning, and the driver can rely on that. And other things like you must set all the points before you can clear the signal, and so on. So this was one of the key things of stopping signals, reducing human error, stopping signals doing dangerous things. I mentioned already about the communication between boxes using the telegraph. This was normally done on a bell system, and in fact this bell system is still used in mechanical signal areas, even though there are good quality phone lines available these days. And these signalers would just press a plunger to operate the bell and send messages between the signal boxes. They normally start with this one ding to call attention, so to wake up the other signaler and make sure they knew that this bell was the one that was ringing. And then they'd send some other messages like ding ding meant a train is entering your sector, or ding ding, pause, ding meant a train is coming out of the sector, and various other ways of saying is a line clear for a certain type of train, and there's other ones for saying is it clear for a goods train, is it clear for an express passenger train, is it clear for an engine by itself, and all sorts of things. There were hundreds of these bell signals used. They also had block instruments, which were using the same telegraph system as the bells, which actually indicated on them whether the line was clear or occupied. And that was an indication that was shown in both signal boxes at either end of that section of line. So they were both on the same page all the time as to what the state of the line was. And this combination of what they called lock and block, which was the interlocking to stop you doing something stupid, and the absolute block, saying only one train was allowed in each section at a time, was actually mandated in 1889. But it did take a little while to come in, particularly on some smaller railways or goods-only lines and so on. Now, if this works, I've got a short video to show what this looks like. So you can see, you can't actually hear, unfortunately, but you can see the signalman there pulling his levers. You can see most of those aren't too difficult to pull. He's putting some stop signals there and putting some back in the frame. Now he's going to go over to the bell, and there's a ring on the bell just then. He's now pressing the plunger to ring it once to call attention and listening to what comes back. And then he's ringing a few other things and turning his block instrument to set the fact that there's a train on the line. And this is all replicated in the signal box at the other end of the section. And what might surprise you is there are still lots of these mechanical signal boxes in operation on Network Rail these days. There were 373 in 2015. That was the last date I could find a figure for. They are gradually being closed. Lots of them are still scheduled currently to be operational into the 2050s. And they're using very, very, very similar technology that was used in the 1800s. There's been some modern developments to add on to it to make it a bit safer in various ways. But the same principle with block bells and block instruments and absolute block is being used in lots of areas. For example, Shrewsbury, the area around Worcester, Malvern, Ledbury, Evesham area in the Midlands, and lots of other areas as well. The biggest mechanical signal box still in use is Severnbridge Junction, which is just outside Shrewsbury Station. You can see just how long it looks there. It has 180 levers. Only 90 of those are in operation at the moment. The other ones are spare. They were for bits of old track and signals that have been taken out. But it's so big you have to have two signalers operated, one at each end of the lever frames. Otherwise, they'd be running up and down the frame and wouldn't be able to do all their work. That's now the largest operating one in the world. And just to give you an idea of what the interlocking looks like, this is the interlocking room underneath it. You can see all these bars are the ones that move into and out of lock with each other to allow you to pull certain levers or not pull certain levers. The closest mechanically signalled box to here is at Marchwood. which is on the line going down from Potton towards Forley. It's a goods-only line at the moment. It's used for taking goods to Marchwood military ports. And so it's only opened when a train is coming there. But you can see a small lever frame there. All along the top here are the various block instruments and various repeaters for signals. And this is the diagram above it showing what each of these levers represent in the real world. So that's the basics of absolute block signalling. You still have a bit of a problem because you know that a train is somewhere between this signal box and that signal box. You don't know whether it's there or there or there. You don't know whether it's somewhere important that you might want to know about it. If it's stopped at a signal, you might want to know that there's a train there waiting for you to clear it. If it's broken down and stopped somewhere, you might want to know where it is. You might want to know if it's on top of some points, because if you try and move the points while a train's on top of it, it's not going to go well. So you kind of want to know where they are. In the original early days, how did you do that? You looked. That's why signal boxes have big windows and are normally up on the first floor. You can look out of the window and see where your trains are, except if it's foggy or snowing or nighttime, which is a bit of a problem. And fog, in fact, was a massive problem. There were lots more fogs in those days with the sort of smog and pea supers and so on coming from lots of coal burning, and that was a massive problem for the railways. So they had this whole special rule in the railway rule book called Rule 55, which says if a train is brought to a stand at a signal, and after 3 minutes, or immediately if it's raining or in fog or snow, the driver must send his fireman or guard to the signal box to ensure the signalman was aware of the presence of the train and that safeguards to protect it have been put in place. And the crewman must then sign the train register, which is a book they keep in the signal box that records all the trains that go past, and make sure that you could record that he was there and said his train was stopped somewhere. And one of the safeguards they could put in place is something called a lever collar. It's a very simple bit of kit. On the left here, you can see a wooden one there. Here, this is a sort of modern plastic one. But it's just something that slides over the lever and stops you moving it, stops you releasing that little catch on the back of the lever to move it. You can just take it off again to move it. Nothing stops you taking it off. The idea is it's there. So when you see it there and you have to take it off, you think, why did I put that there? There must have been a good reason. And hopefully that stops you just taking it off and doing it willy-nilly. It makes you think about what you're doing. Fortunately, that doesn't always work. And this is where we come to the UK's worst railway accident, Quinton's Hill, in 1915. It killed over 200 people, injured a similar number. And unfortunately, a number of the people killed were troops going off to the First World War. So they got killed before they even got to the battlefield. And I've got some little diagrams here to show you how this worked. This was the main line up in Scotland. So this was going this way on the top line here was going to Carlisle. Going this way was going to Glasgow. Here's the signal box. And you've got a goods train in the siding here. This was quite common. You had lots of goods trains in those days. They were very slow. So you shunt them out of the way into a siding to let the faster trains go past. The first train that comes along is this orange train, which is a local passenger train. And it comes along and he wants to shunt it out of the way somewhere. He hasn't got that siding because that siding's got a goods train in it. So he shunts it back onto the other running line. That's a bit unusual, but not against the rules by any means, because they had lots of extra traffic because of the war and they needed somewhere to put trains. So as long as he remembered that train was there, it was fine. Unfortunately, even though he travelled to work in his signal box on that train and had literally just got off it outside the signal box and gone up into the signal box to do his job, he shunted another train out of the way and then cleared the signals for a train to come on that main line down to Carlisle, which crashed into the train that was there. Now, what you'll find often happens in these railway accidents is you've had an accident, the carriages are all skew all across the track and they're blocking the adjacent line. So the next train, which has already had clear signals, comes up from Carlisle and crashes into the wreckage. And that's what you often find, unfortunately, there's a big issue with trains that have crashed obstructing other lines. So why did this cause? Well, the signalman just forgot about the train, even though it was the train he arrived on. The driver of the train that was there did do Rule 55. He came into the signal box, told the signalman he was there. Unfortunately, the signal box was being used as a bit of a social centre at the time, and there were about half a dozen people in the signal box chatting amongst themselves, which wasn't ideal. But he didn't check the signalman had put a lever collar on when he should have done. And there were all sorts of other things going on. They agreed between themselves to change shifts at different times and hadn't told anyone and were falsifying the records, and lots of other things going on. But principally, the signalman forgot about the train. So what can we do to try and stop that? Well, one technology that started to be introduced after that was track circuits. The idea with it is you take your railway track here, you take some kind of power source, a battery or some other kind of power source, and you send electricity through both rails of the track. And then at the other end of your chunk of track, you connect those to a relay, which detects whether there's any electricity getting there or not. So you basically see, is there any power at the other end of the track? And if there is, then you know that the track is empty because all the power is getting through the track. If, however, you put, if however you put some wheels on the track here, wheels are metal, they conduct electricity, so the electricity will get short-circuited through the wheels and go back to the battery. It will never get to this end of the track. So in that case, it won't energize this relay, and you know that there's a train on the line, and so you need to make sure that you're careful because there's a train there. And that technology is still used these days, and there's various complicated forms of track circuit nowadays, but the same principle is used. And they can then be electrically interlocked. So when you've got this mechanical interlocking that stops you pulling conflicting levers, you can add a few electromagnets in there connected to the relays and stop them moving when there's a track circuit occupied. So, for example, this is how the diagram would look. These little black lozenges would light up with little lights behind them when the track circuit was occupied. They'd also be interlocked so that you can't clear the signals onto a bit of track if the track circuit shows the train already on that bit of track. And also, you can't move points when a train that shows a track circuit over the points shows that a train is over those points. Both really useful things. And they were only installed in some places, and they're still not installed across the whole network, mostly in the early 1900s and developing beyond then in sort of high-risk locations. Interestingly, this is why leaves on the line are such a problem for railways. You've always heard about the excuse of wrong sort of leaves on the line. Well, there's two problems that leaves cause. One is that leaf residue on the line is slippery, so it causes trains having difficulty to stop. And if the train can't stop in time, they might go past a red signal and cause an accident. And the other thing is that this leaf residue on the track insulates the track from the train wheels, which means those train wheels won't short circuit the track anymore because they're insulated from it. So that means that you can have a train that disappears from track circuits because its wheels are insulated and it disappears from the signalling system's view. And that's why it's so dangerous. And one way they get around this these days is something called the railhead treatment train, which is a train that drives around the network with multiple trains that drive around the network during the autumn season, blasting really high pressure sand and water mixture onto the track to blast that leaf residue off so that you don't get that insulating effect or that slippery effect. As an alternative to track circuits, and something that's being used more often these days, now they've become more reliable, is something called axle counters. And they're just attached to the track. They look like this, and they use electromagnetic induction to count the number of wheels that go past them. So what you do is you have an axle counter at the beginning of your block section, and an axle counter at the end of your block section, and you count the wheels in and you count the wheels out. So if your train had 47 axles on its way in, then if you've counted 47 out, you know that there's nothing left in the section. So you literally just do the subtraction of you add up the ones in, subtract the ones out, and if it ends up at 0, you know that your section is clear. This has some advantages and some disadvantages to track circuits. It was originally applied in areas where track circuits behave very poorly, like wet areas, like tunnels. But now most modern re-signalling schemes on the UK railways are using axle counters for a good proportion, if not all, of the train detection methods. Unfortunately, though, axle counters did cause one accident in the Severn Tunnel in the early 90s. Luckily, nobody died, but there were some quite serious injuries. This was when two trains ended up colliding with each other in the middle of the Severn Tunnel, which was obviously a bad place to collide because it'd be more difficult to get rescue help there and so on. And it's still not quite understood exactly what caused the accident, but it seems there was a signalling fault at the time, so there were special arrangements in place for signalling trains. And signalling technicians were also having to try and investigate what the fault was. And it seems likely that they went into the interlocking room and pressed a button on the axle counter that reset it to 0. And of course, if you reset the axle counter to 0, it thinks there's no train in the section, but there actually was, so it then cleared the signal for the next train to come through, and they collided with each other. That is disputed depending on who you ask, and the people who supposedly did it swear blind they did not do it, but that seems most likely. Another development for signals, moving from these mechanical semaphore signals to colour light signals, which are the sort of signals you see in most places in the UK these days. The benefits of these were really that they would give you more information than just stop or go. They had what's called multiple aspects, and we'll come to those in just a moment. And the other benefit is that you can control an electrical signal from a lot further away than you can pull a physical wire attached to a mechanical signal. So you can concentrate your signal boxes in big locations rather than having them spread out all over the track, which means you need less people to operate them, and it's cheaper. And these were installed really quite early in the 1920s on the southern region, which was very early with colour light signals. In most regions, they didn't really come in until the 50s, 60s, 70s, sometimes even 80s. And I say some areas don't have them now. The sort of way this worked with multiple aspects was you could have a red signal, that meant stop, as you would expect. You could have a single yellow signal that meant the next signal will be stop, so slow down. Just like a distant signal in semaphore signaling. You could also have a double yellow signal, which meant the next signal will be single yellow, and therefore the signal after that will be red. And that was because trains were going even faster these days, and they needed longer and longer to slow down, so the driver needed more warning. And then you could have green that was go. So if you picture what it would be like, if you put a train right in the distance here, just behind the train would be a red signal saying stop, don't hit the train in front. Before that would be a single yellow, before that would be a double yellow, and before that would be a green. So you can get much more control over what the driver is doing and give them far more warning. Now, because you were using electricity to control your signals rather than wires, you didn't have to have a big mechanical lever to give you that leverage to actually pull a wire. You could use mini lever frames. They weren't that common, but actually one of them was taken and used in Liverpool until very recently, and you could flick them. They were the kind of things you could flick with sort of half a hand, just to flick, 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 far better than running up and down a frame and pulling these big heavy levers. And they had electrical indications of what the signals were showing on them as well. But what was far more common in the 60s was introducing things called NX panels, which are entrance-exit panels. This is the Swindon panel, NX panel, and this single panel replaced 40 signal boxes on the ground. If you consider those 40 signal boxes would have had to have a signaller operating them in maybe 3 shifts of 8 hours each. So that was 3 signallers a day operating 40 signal boxes. That's a lot of staff. You could replace it with Swindon panel was operated by 2 signallers, occasionally with a third to help them. And this was 80 miles of track, and they moved from this absolute block method where they're communicating between all these 40 different signal boxes to something known as track circuit block, where the whole area was track circuit, not just bits of points and bits of high risk locations, but the whole area, so you knew exactly where your train was at any one time. And this is what the panel looked like. All these black lines are tracks. The red bits are lit up where a train is on them, according to the track circuit. And the white bits are lit up where you set a route for a train from one place to another. Because the reason these were called entrance-exit panels was that you didn't have to control every signal at every point by itself. So if you were on a mechanical signal box and you wanted a train to go from here to here, you might have to pull 5 signals and 3 points to get it from there to there, or even 10 signals and 5 points or something. Here, you would twist the little knob at the place you wanted the train to start from, and press a little button at the place you wanted the train to go to, and it would set all of the points and all of the signals between those automatically, and then show this set of white lines to show that a route was set over that area. It reduced the signaller's workload massively because they could just say, train from here to here, please, rather than pulling 20 levers. If we zoom in a bit, you can see this is a little twisty knob. You had some other regions of British Rail had little buttons rather than the twisty knob, and this is the button for the sort of exit. So you twist the knob and then press the button further on. This is what's used on the local railway around here, an entrance-exit panel called Eastleigh Panel. If people know Eastleigh Station and the Lidl that's just north of Eastleigh Station, there's also a Marks and Spencer's food there now. Well, this is the Marks and Spencer's food just here. Lidl is just down here, and you've got the main line going up to London and the branch line going off to Chandler's Ford. And in the gap between those lines is the buildings here, and in there is Eastleigh Panel, which looks like this. So it's the same approach as the Swindon panel I just showed you, except all the controls are up vertically rather than kind of down horizontally. They have 4 signallers working there, well, 3 signallers and a shift manager. And you've got all the track here from Winchester up here, going right down through Southampton out towards Cockenhurst. You've got the Chandler's Ford branch down here. You've got the branch over to Woolston down here as well. So that's all within one area where it would have been at least 40 or 50 signal boxes beforehand. How do these signal boxes work? Because we had this mechanical interlocking that physically stopped you pulling levers. How's that going to work for an electrically signalled layout? You switch from using mechanical bits of metal that hit each other, doing it all with relays. So you will have a room under your panel, a massive room, filled with all these relays. These are big safety critical relays, so they're very carefully designed, but always fail safe and work in particular ways. And you connect them all together electrically so that the electrical signal that you use, it basically replicates logic gates in the relays, which allow you to do certain things and not do other things. So when you press your buttons on the panel, if it can't do that route, it will flash lights at you to say, this isn't going to work, sorry, and you can try a different route. And if you stand in one of these relay interlocking rooms, as I have done when someone's using the panel, all the relays make clicks when they operate. When someone sets a route on the panel, it goes click, 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 click. And then when trains go over into an area, you hear the click, click, click of the track circuit relays going as a train enters the area, click, 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 as the track circuit relays go again when the train's exited that section, and so on. It's quite an atmospheric experience in those relay routes. Unfortunately, even with modern technology like this, you can run into problems. Some of you from this area may remember the Clapham Junction accident in 1988. It was a train that came up from Southampton direction, one of the trains that was involved in the accident. And this is what happened. You had the railway here, Southampton at this end, London at this end, and a train came going along the line and saw something it could never see. If we go back and look at that again, the signal was green, and just as he got to it, the signal turned red. That shouldn't happen. He should have had a yellow signal in advance to warn him. There's no way you could suddenly stop going at 80, 90 miles an hour or whatever. So he stopped at the next signal, even though it was green, phone the signaller and go, what's happening? This shouldn't have happened. Everything okay? What's going on? Unfortunately, while he was on the phone to the signaller, this red signal behind him incorrectly cleared to show a yellow. So the train behind him came straight up and went straight into the back of him. And then, as I said, it's quite common, the train came in the other direction before anyone could warn it and went into the wreckage. Now, this happened because there were signalling upgrades taking place in the area, and there was what's called a false feed. So someone had left a wire connected in the relay room that shouldn't have been connected. Reports vary as to whether it was actually connected or whether it was just a bare wire that was floating around that happened to come into contact with a terminal. But you can imagine if you've got easily 10,000 relays, they all have to be wired together. It's very complicated to get the wiring just right. It meant the relay was powered regardless of whether a train was there or not. They didn't notice it when they tested it because there weren't many trains around. As soon as it got to the next morning peak services where you have lots of trains coming into London, trains running close enough for it to cause a problem. But the real reason was that the signalling technician had been working 7 days a week for 13 weeks and was massively overworked and overtired and wasn't checking his work. We had made a mistake and there wasn't enough checks on his work. It should have been wire counts done at every relay to make sure the right number of wires were plugged in. There weren't. It should have been someone else checking all the wiring diagrams. There wasn't. So after that came in lots of changes in something called the hidden report, which was the public inquiry into the accident, and that recommended working hours limits that still apply. They're called the hidden limits, mandatory testing of these things, and they gradually started moving to solid state interlocking, which is computer-based interlocking, where you can't have stray wires. You can have, of course, bugs in your code, which is that whole separate issue. And also did more work on radio communications with trains, because as you know, the other train came into the wreckage. If you could get a message to that other train in time, that train could do an emergency stop and hopefully not crash into the wreckage, or at least not crash into it going as fast. Interestingly, there was a very similar, very minor accident at Waterloo in 2017 that was caused by very, very similar reasons, which is a bit worrying. This was the result of the accident. They were doing some work at Waterloo at the time to extend some of the platforms, and very sensibly, they put one of their empty trains that had carried ballast or something in there as a kind of blocker in between the live bit of the station and the bit that was having work done on it. But as you see, this train went into the side of it because the points were set incorrectly. And that was because there had been some unauthorised changes to the wiring in the relay room, and no one had done enough checking to realise that these unauthorised changes were still in place. Unauthorised changes were done with the best of intentions to help with the testing, but they weren't checked and they weren't authorised. They should still have been noticed, and they weren't. We've talked a lot about signaller error and signallers forgetting about trains, but of course you can have driver error as well. A driver can go past a signal he shouldn't do, and it's known as a SPAD, a signal passed at danger. And there's quite a lot of them happen on the network. Relatively few if you consider how many signals there are, but there's a few dozen at least every year, most of which don't lead to anything particularly disastrous happening. But unfortunately, some of them do lead to disastrous situations. And one of these was Harrow and Wealdstone, which was the second worst railway accident in the UK in 1952, killed over 100 people, injured a lot. And this one, there was a train in Harrow and Wealdstone station, and another behind the train were two semaphore signals, both at danger, and the colour light signal at caution. And the train came along and went straight past all three of those and into the back end. And then, of course, another train came into the wreckage and crashed into it there. Why did that happen? We have absolutely no idea. The driver and fireman were both killed. We don't know. They were both experienced drivers. It had been a bit foggy, but it wasn't very foggy at that particular moment. All the other trains going past had seen the signals properly. They had no particular indications of wanting to commit suicide or anything. Nobody knows. But they passed the signals, and that led to a massive accident. So after that, was installed something called automatic warning system. And the way this works is you have a little, what's called a ramp in between the rails that has some permanent magnets and some electromagnets. And the electromagnets are either energized or not, depending on what the signal is showing. And this combines with some detector equipment on the train that detects the magnetism from the magnets. The upshot of which is if you pass a signal at anything other than green, it will sound the bell in the cab and display this thing that's called a sunflower, this warning dial called a sunflower. You then have to press a button in the cab to acknowledge that warning within something like 3 seconds. And if you don't, the brakes will automatically come on. And this was introduced from the 50s. Took a while to be introduced in some areas. It's at pretty much every signal now. And it still works in the same way. You can still have exactly the same indication, occasionally these days displayed on a computer screen, rather than that if you've got a very modern driving cab. It warns you when the signal is not green. The problem is, of course, that a lot of the time signals aren't green. If you're going into Waterloo or somewhere from here in the rush hour, you're never going to see a green signal because there's trains spaced all along the track trying to get into Waterloo in the rush hour. So every time you go past a signal, you'll be pressing the button. And it's very easy. Just get used to, oh, bell, press button, bell, press button, bell, press button, and forget that you're actually meant to be taking account of the fact that, yes, that button means you're meant to be slowing down or stopping or whatever. And some of you also may remember the Ladbroke Grove accident in 1999. This was coming out of Paddington Station going northbound. And this was in an area that did have AWS fitted. And you had a red signal that train 1 was coming to, and there was a crossover here. We were waiting for train 2 to come across the crossover to go into Paddington. Train 1 was coming out of Paddington and meant to be going along this track here. But at that point, because this was set red, the point had still been pointing that way, and the train went past the signal into the package there. So this had AWS. The driver was warned, but he acknowledged the warning and carried on driving anyway. There were a number of other issues going on here. it was a frequently spadded signal. Also, it had been passed at danger 8 times in 6 years, which is quite a lot. It was difficult to see the signal as you were coming along the track. There were lots of signals above the track. Trying to work out which one applied to your line was quite difficult. The driver hadn't been trained very well. He hadn't been warned that this was a particularly troublesome signal, which he should have been. And also, they didn't have something called flank protection. The layout of the track there had been designed to have flank protection, but there'd been budget cuts and it hadn't been implemented. And flank protection basically means that when a train is coming along here, these points should always be set in a way that means that it couldn't crash into something else. Even if these points weren't needed for anything else at the moment, but they were still set the way they had been. Whereas flank protection would mean they were always set in the way that would be least dangerous if a train passed a signal at danger. So in this case, they would have been set straight ahead, then the train would sail along here and wouldn't have crashed into anything. So after this, they started introducing something called PPWS, which was the next version of AWS, a better way of stopping trains if they go past signals of danger. And these use little loops in the track which transmit radio signals to the train. And the train will come along and you'll encounter a number of these loops at different stages before the signal. And so that can also not just stop a train if it goes past the signal, but it can detect maybe 300 meters before the signal that the train is going too fast to be able to stop at the signal, based on what they know about trains braking, and therefore start the emergency stop at that point, which means hopefully when it's done its emergency stop, it's still stopped by the signal. Because of course, if you wait to go past the signal before you start doing your emergency stop, it'll take you another few hundred meters to stop and you'll be past the signal and possibly hit something else before you've stopped anyway. Again, it took a long time to get funding for this and get them all installed and so on. It's now at all what you call high-risk locations. Basically, all locations where you have a reasonable chance of hitting something else if you go past the signal. So junctions and the end of single lines and so on. And it's led to quite a reduction in fads. So what does really modern signalling in the UK look like? Well, gradually, just as the mechanical signal boxes were replaced by the panels are being replaced by computer-based signalling. They work in exactly the same way. This is a signaler's workstation at the Thames Valley Signalling Centre, which now controls a massive area of track from Paddington to Bristol, Paddington to Oxford, Paddington down towards Westbury, plus a bit and slightly randomly of Cornwall as well. The idea was it would eventually cover the whole of the Western region, but that's kind of been shelved because they didn't have enough space to put all the signalers in one building. And you have the slight issue of what happens if there's a fire alarm at the building. You just stop all the trains in the whole of the western area of England. Anyway, they have lots of screens, but the screens are replicating what you would see on a panel. So in this case, you use a mouse or a trackball to click on the signal at the start and click on the signal at the end, and it sets the route between them. However, you do also have something called automatic route setting, which in normal operations, when your trains are running normally to a timetable, will automatically set up the routes for each train. So theoretically, all the signaller has to do is sit there and watch those routes being set up and check it all works in the right way. You can take over and start setting routes completely manually if there's disruption or things are going wrong, but theoretically it reduces the signaler's workload. In practice, because signalers have to be able to do all of the manual stuff if automatic route setting fails or if there's disruption on the timetable, it doesn't actually reduce the number of signalers you need because you still need to have enough signalers to do it all manually in the event that you might need to. But it does allow signalers to concentrate on other things like crossings or bits of engineering work happening on the track or whatever. And then the real endpoint of railway signalling is in-cab signalling. So getting rid of these pesky line-side signals and communicating directly to the train, you have the authority to proceed at such and such a speed until such and such a point, at which point we will say, no, you're not allowed to proceed anymore, and then we'll give you a new authority to proceed to a different place. And this is how it will be displayed in a cab. There's a little indicator, a little screen here. This is a kind of strip map of the railway showing where you've got authority to. This will be a speedometer that will show you what your target speed should be. So it tells you how fast you should be going to be able to stop in time, and it monitors what you're doing. So if you start going too fast, it will slow you down. And the way this works is about these things called balises, which go in between the track they send little, they're passive radio things, so they send message, the train activates them if they go over, it sends a radio message back to the train saying where the train is on the track, and then the train uses mobile signal, GSM-R it's called, which is the same system that your phone uses, but a railway specific version, to send these bits of instructions to the train. One of the benefits of this is you can move from a fixed block system to a moving block system. Remember we talked about absolute block in the early stages of this talk. And although we're not using absolute block anymore, we're still using these block sections between signals, and they're all the same size. That can be inefficient, because the reason they have to be quite big is because trains have a poor braking habit. They take a long time to slow down. So if your trains are going fast, you need big block sections. If your trains are going slowly, you don't need big block sections, because the trains can stop a lot quicker when they're going slowly. So you can fit more trains into a space if you make your block sections dynamic and vary their size and location based on what the trains are doing at the time. So that's called moving block. And then the final stage of this is you've gone from getting rid of those pesky line-side signals, now you get rid of the pesky driver, and you have automatic train operation. And we've had this in the UK for a long time. The Victoria line in London on the Underground was the first automatic train operation system in the UK before the Docklands Light Railway, which everyone talks about as automatic train operation. It has a driver. The driver's job is to press this button, which says automatic train operation start. And so he closes the doors, presses the button, it drives itself to the next station, he opens the doors, closes the doors, presses the button, opens the doors, and that's his job. Obviously, he also deals with emergencies and can take over manual control and so on. But this is all controlled automatically by the signalling system, so the train does exactly what it's told. And the Docklands Light Railway took this a bit further and got rid of the driver entirely. They have a member of staff on board for safety purposes. He's not doesn't have to be at the front of the train, doesn't have to be looking out or doing anything about driving. And that used moving block system since the early 90s. So these things have been going for quite a while. It's just getting them into operation on mainline high-speed passenger railways that aren't kind of self-contained like the Docklands Light Railway is the challenge. We're pretty much finished now. I just want to point out the amazing variety of signalling you see here in the UK these days. If you were to travel from London to where I grew up in Malvern, in Worcestershire, near Worcester, you could have a lot of different signalling systems controlling you on your journey. You could start off on the Victoria line in London Underground on automatic train operation. You then go to London Paddington, which is controlled from Thames Valley Signalling Centre with a computer-based signalling system, with computer-based interlocking behind it. You then get to Oxford, which was controlled by a panel, like it was installed in the 60s or 70s. And you then get to Worcester and Malvern itself, which is controlled with mechanical signalling with the same signal boxes that were there in the 1800s, all in one 3-hour train journey. So that's the end of the talk here. If you want to find out more, there's some good places you can go and learn more about this. There's the Bondi signal box locally, which is a preserved signal box where you can go and operate levers, learn more about how they work. The Swindon panel that I showed a picture of earlier, the long panel there, is preserved at Bigcock Railway Centre. I was one of the people who was involved in preserving it when it was stopped being used by Network Rail about 6-7 years ago. The Midhants Railway, quite local here, has lots of mechanical signalling. In fact, that's some of the pictures I used from the Midhants Railway. If you want to learn more about accidents, there's a great podcast called Signals to Danger that takes you through a load of these accidents, including some of the ones that I've talked about in a lot more detail. But in the meantime, thank you very much.
I'm going to leave it to Robin to respond to the questions when this microphone's on, as he's got a big pile of them. And I was just said we haven't had anything like that in questions since we went to the post-it note system. So, Robin, over to you.
Hi, thank you. So I'll go through these in no particular order. I think only one question has been duplicated amongst these, so that's quite impressive. Someone asks, what's with the cloth used with old signal levers? Did they use a cloth with the electric signals? So the cloth was mainly, it was sort of the signalman's badge of office in some ways. It was to stop the oils from your hands rusting or corroding the metal tops of the levers. But right back from the Victorian era, there was a real focus on cleanliness in signal boxes, and there'd be rotors for which shift would polish the levers and polish the bell plungers and sweep the floor and relay the fire and all this sort of stuff. There's a big focus on cleanliness next to godliness and so on. But mainly for stopping you rusting the levers and ending up rusting the mechanism that uses a little catch to release the signal. They use them with electric signals. The small lever frames, I'm not sure if they did or not. I've never seen them being used with the small electric lever frames. Sorry. I've never seen them being used with those, but I suspect they probably might have been. I'm not sure about that one, to be honest. Someone else asks, is the so-called dead man's handle the same as AWS or related to it? So no, they're completely separate systems. The dead man's handle is something where you will get a little buzzer go off in the cab every so often, and you then have to press a button or a lever within a certain amount of time. If you don't, then it stops the train. That's to stop you if you've collapsed or gone to sleep or whatever. That's completely separate from AWS, because a dead man's handle can happen regardless whether you're going past the signal or whatever. And it will be different noises, so you know what it is, and also a different button to press, mostly, to acknowledge it. Are drivers distracted by mobile phones? So, as a driver, you're not meant to use your mobile phone while you're driving, a bit like in a car. It is known to have happened. There's one quite sad story, actually, about a fairly minor accident that happened in March 2020. I can remember when it was, because it was the day that lockdown was announced. And there was a freight driver driving his train up in Bromsgrove area, I think it was. And that afternoon or evening or something, the Prime Minister had been on the television announcing that there was going to be a lockdown and schools were going to be closed and all of this sort of stuff. And he was really worried, because he knew he was an essential worker and he was going to need to carry on driving his freight train. But he couldn't work out who was going to look after his children. And before he came to work, he was trying to talk to his wife and his ex-wife and all sorts of complicated things. And so he ended up continuing doing that while he was driving his freight train. Sending and receiving text messages when he was waiting at signals and so on. And it was a combination of using the mobile phone, being distracted. I don't think he was actually using it at the time, but being distracted by the whole process of being in communication with someone else, that he ran through some buffer stops at the end of the siding and ended up, which was not great in the sense the train derailed onto the palace. It didn't kill anyone or anything. Unfortunately, the position his train ended up in was slightly foul of the main running line that was next to the siding. So when the next passenger train came along, it clipped the edge of the locomotive and damaged itself. Again, no one was killed. I don't think anyone was injured, or at least not more than a few cuts and bruises. But it shows how distracting these things can be. It also shows he was in a very difficult situation, and the effect of announcing some massive change like that can have a big effect on someone who's then meant to go and do a safety critical job. Are drivers tested for colour blindness? Yes, and they have been for donkey's years, right back from the Victorian times. There were very, very stringent medical tests, particularly eyesight tests, but general medical tests for drivers, for signalmen, for guards, for porters, for all sorts of railway staff in those days. You cannot become a driver if you're colourblind. You can become a driver if you wear glasses and things, as long as you've got good enough distance vision and you always wear your glasses when driving and so on. But yeah, there's very, very stringent tests, and drivers will have a medical, at least, I think it's once a year, they have a medical, they have to alert the company if they're taking any medication whatsoever, and it has to be checked by the company's doctors to make sure it won't affect them. All that kind of stuff. They're very, very highly regulated. So, in the very automated signal control centres, how do you stop the signalman from going to sleep? Yeah, I mean, it is a problem if everything's being done for you. It's a bit like modern pilots can have problems where the planes fly themselves so much of the time that when they suddenly need to take control, they don't know how, or they have to suddenly switch from very low alertness to very high alertness. It's difficult. What I will say is that a lot of other things take up the signaler's time as well as actually signalling trains. So if you've got automatic route setting up your routes for you, that doesn't mean you've got nothing to do, because apart from monitoring that, you'll also get lots of phone calls. Signalers get loads of phone calls these days, and that might be from someone at a private crossing saying, I want to cross with a herd of cows, is there space for me to cross? Or I want to cross with a big lorry. It might be people working on the track who are calling to say, can you stop the train for 10 minutes while we fix a bit of track? Or all sorts of things like that. Or people from the control centre, the main control centre for that railway company, phoning up to say, how are these trains running, or can you do this particular type of regulating of the train to sort it out, or whatever. So there is quite a lot of other stuff going on. It must be said, however, that this isn't so much going to sleep, it's more of a kind of discipline type thing. A lot of people have been moved relatively recently from panel signal boxes into the big kind of fairly anonymous computer-based signalling centres, and they aren't particularly happy about it. There's been quite a lot of morale issues. Similarly, a lot of people, when they moved from mechanical signal boxes into things like panels, didn't like it, because in mechanical signal box, you were right by the track, you saw the trains go past, you often ended up interacting with drivers quite often, all that kind of stuff. A lot of that was lost when you were in a panel room, which might be near the track, but it's got no windows looking out onto the track, so you can hear the train, but you can't see it. You're not doing anything physical anymore. A lot of people didn't like it and left the industry at that point. How long did it take to update the mechanical interlocking when a track was changed? Is it any quicker with modern systems? If only it was. So, I mean, trains were originally designed to have spare levers a lot of the time, so that other alterations to the interlocking could be done fairly easily. So you'd have a 30 or 40 lever frame, and maybe 3 or 4 of those would be designed as spares to be then brought in when you add a new siding or whatever. In terms of doing the interlocking, they had massive numbers of staff in those days. The railway companies sometimes did their own interlocking at their own works. Other times they contracted out to signalling contractors. Mackenzie and Sons was one of the big ones. Westinghouse was another one. It could happen pretty quickly, because actually it needs someone to design it. Then it just needs someone who can use metalworking tools to chop and cut up the metal in the right way. These days, for changing some of the electronic systems is quite difficult. The panels aren't too bad. The panels are often, they're called domino panels. They're made up of lots of individual little tiles. So you can take the tiles out and put new tiles in and then wire it all up. And that's quite easy to change. You don't have to change the whole panel at once, at least not on most of them. With the electronic stuff in computers, theoretically it's simple to change, because you just have to change a few lines of code or add a new graphic into the thing or whatever. But it then needs a huge amount of testing to make sure that you haven't accidentally introduced any bugs. The other thing is that mechanical interlocking, you have to have someone who knows how to design it, because and actually they've had to bring those in from overseas now for network rail, because they haven't got enough of them left in this country. But actually to make it, you see someone who can cut and shape metal. Whereas if you've got an electronic system that was designed by a company that's gone out of business, you have to find someone else who understands that system and wants to modify it. So what tends to happen is the company stays in business nominally and charges you an absurd amount of money to do any changes. So Bournemouth is controlled by a solid state interlocking, a computer-based interlocking. And they wanted to do some minor change. I can't remember what it was. It wasn't even much to do with the interlocking. It was, changing a bit of text on the screen or something. And they were quoted, £750,000 for doing it. And so it never happened. It's because the company knows they're the only ones who can do it, so they can milk them for whatever they want. Were red for stop and green for go innovations when they were introduced, or were they adopted from elsewhere? That's a very good question. I've no idea, but I'm going to go home and look that up. I don't know, I'm afraid. I guess red has been a sort of stop/warning thing for quite a while, but this would have been before traffic lights and things. So I don't know is the honest answer to that. Sorry about that. If you've got a signal box controlling a large area, what if the computer system fails or there's a fire? A huge area would then be at a standstill. Is this wise? Depends who you ask as to whether that's wise or not. It's not. Yeah, it can be a problem if you've got Thames Valley Signalling Centre and the whole of Thames Valley Signalling Centre goes out. Then that's most of what used to be the Western region of British Rail. So all the main line from Paddington to Bristol, possibly even over to Cardiff now. I'm not sure where it goes up to, and all the way down to Westbury and all the way up to Oxford, all at a standstill, because if the signals aren't in the building, they press a button, so there's an emergency button that says all signals on, which puts them all to red, and they can leave the building and it's safe, but everything's stopped. One interesting thing with Thames Valley Signalling Centre, they've obviously got a sort of best room for the signallers, which has got a little kitchen, and they very sensibly have separate electrical circuits for the safety critical signalling stuff and the kettles and toasters. Except when they were installing them, they muddled them up. And so the first time that somebody burnt a bit of toast and tripped the circuit, they turned out that half the signaling system went off. They learned from that fairly quickly. And they do have backup power supplies and fire systems that mean you don't have to leave the building as soon as the fire alarm goes off. You have like they do in hospitals, and they have staged evacuations and so on. So they've got all that stuff. But yeah, if a bomb hits Thames Valley Signalling Centre, then nothing's going to move on the Western region for quite a long time. And in the old days, actually, with the panels, they used to have backup panels occasionally at different locations. They didn't do the full things that all the panels would be. They wouldn't be entrance-exit panels. They'd be what's called individual function switch panels, which are more like a mechanical train in a panel. So they'd have an individual switch for every point and an individual switch for every signal. But it meant that you could send a bloke to go to the spare panel that was in the back of a relay room in Bassett or something, and they could sit there flicking switches as controlled by as told to by the signaller over the phone, and you could at least get some things working. Talking of Wootton Bassett, someone's just written near miss Wootton Bassett. This is quite an interesting story. This was a I can't remember when it was. It would have been 2010, 2015 maybe, something like that. This was a steam special, so it was a steam tour, steam locomotive on normal network rail, national rail lines. And it was coming through Wootton Bassett, and it did a massive signal past at danger, which missed another passenger train by something like 5 seconds. And because it was a steam charter, it was using heritage rolling stock, so it was using heritage carriages, which are not particularly crash worthy. So if it had crashed, it would have been really nasty. And that happened because the people on the footplate had disconnected the safety systems. So these obviously on modern trains, it's very difficult to disconnect the safety systems because they're integrated into the whole train and the whole cab right from the get-go. With an old steam locomotive built in the 50s or something, they've had to retrofit the safety systems like AWS and TPWS and so on. And so there was a way to find the right switch or the right fuse box to just turn off TPWS. So this happened. They got I don't know whether it was TPWS or AWS rate demand. So they hadn't acknowledged it quickly enough. The bell had gone off. They hadn't pressed the button within 3 seconds or whatever, which is kind of understandable because you've got a lot of things to do on a steam locomotive footplate. If you're busy firing and busy doing things, you might not get there in time. But rather than letting the brake come on, coming to a stop, contacting the signaller saying, "I'm terribly sorry, I missed the AWS," having it as a black mark on your record, but then the signaller filling in a form and saying, "Right, off you go, start again," and so on. They decided to disable the system, which stopped the brake demand, and they carried on. And this was a footplate that, because it was a steam locomotive on network rail metals, had not just the driver and the fireman, but also a locomotive inspector on the footplate. And the locomotive inspector was either the one who disconnected it, or at least was fully aware it was being disconnected. I believe they were prosecuted. I know definitely those drivers and firemen aren't working anymore. They very, very nearly, it got very close to Network Rail banning all heritage traction on Network Rail tracks, because it was so close. If that had happened, it would have been one of the big disasters. It really would have been. So that was nasty. What else have we got? How does our mixed system relate to European practice? That's a very good question. European practice, they do have mechanical boxes and things still, probably not to the same extent that we have here, partly because the railways came later and we were the innovators in the railways, we brought these things in first, and other places came a bit later anyway. There's also the fact that a lot of the railways in Europe were significantly destroyed in the Second World War. I mean, the British railway system was badly affected, but the railways in France, for example, were not just bombed by the Germans before they invaded France, but they were bombed by the British when we were about to invade, Normandy landings and so on. They were really, a lot of them were wiped out. So they got some benefits from that. Because when they rebuilt them with more modern signalling, they rebuilt them with electrified lines. We've got far more electrification of railways on the continent than we do here, because of the fact that so much of the railways were destroyed. They had to start again, and if you start again in the 50s, you start with electrification, which you don't start with obviously when you start in the 1830s or something. There's various plans at the moment to try and unify European railways a bit more. Something called the European Train Control System, ETCS, and ERTMS, which is the European Rail Traffic Management System. The idea of which is to have interoperable signalling between different places, which is based on sort of more modern moving block techniques. The idea would be that you could have eventually, supposedly, if it ever happened, a train with the same signalling system starting on the UK network, running through the Channel Tunnel, running into France and Germany, and so on. At the moment, trains that do that have to support multiple different signalling systems. And in fact, that's one of the issues with Crossrail in London, which has opened, as most of you know, relatively recently. It was very significantly delayed. One of the reasons it was so delayed was because the new train that would operate on Crossrail, because Crossrail goes from Reading in the west through into London Paddington, then through the new underground section and out into Essex at the other end. There were three or four different signalling systems that the train had to operate with. The traditional signalling system out of Paddington, the special signalling system they used going up towards Heathrow, the modern signalling system with automatic train operation for the middle bit, and the old heritage signalling system at the other end. And getting the train software to work with switching between all these different signalling systems while you were going at 80 or 100 miles an hour was really difficult. And that was one of the big integration problems with Crossrail.
We've possibly got time for one more.
Okay, one more. Have a look at this one. You mentioned level crossings once in passing. When operated from the adjacent signal box, issues can be seen and dealt with, e.g. a barrier failure or a vehicle still in the crossing. How can signalmen miles away know this and deal with it? So there's many different types of level crossing as you can shake a fist at these days. The list of them you can find online, and it's about 20 different types in the UK. The two main types really are automatic half barrier crossings. So they don't have barriers that go across the whole road. They just go over that particular lane of traffic, which means if you get stuck in the middle when the barriers come down, you can swerve around the barrier to get out. You won't be trapped on the track. And those are not controlled by the signalman at all. The signalman will have an indication saying the crossing is operating normally or the crossing has failed. That is it. They're not linked to the local signals at all. They are just controlled by a treadle, which is something or similar on the track, which is something pushed down by the train as it goes past, which starts the crossing sequence. The crossing sequence takes a certain amount of time, and so on. It's all done automatically with no signaller involvement. The other type of crossing is various different sorts of crossings with signaller involvement. So, for example, those of you who know Mount Pleasant level crossing in Southampton, it is, I guess, in sort of northern Bevis Valley kind of way. This is Mount Pleasant level crossing, so it's got full barriers across the road. And so you have to be sure that there's no cars on the crossing when you close the barriers, or they won't be able to get out of the way of the track. Or in fact, the barriers are designed that if you hit them hard enough with a car, they'll brake deliberately to allow you out. And so they have CCTV there, and the signaller at Eastleigh Panel has a CCTV image of Mount Pleasant level crossing, and before he can clear the signals that protect the crossing, he must look at the CCTV image and press the button to say yes, the level crossing is clear. There are all sorts of other variations on that. There's automatic obstacle detection that uses radar and things to try and detect if there's any obstructions. And then most commonly, in some ways, a vast number of level crossings are like this, are the little level crossings for private tracks, farm tracks, and things that cross the railway, things that you can't get rid of because they were there before the railway was built back in the 1800s. And they have manual gates and a phone for the signaller. You have to stop, you have to pick up the phone the signaller, say, can I cross now? The signaller will say, well, how long will you take to cross? Are you taking 50 cows across, or are you just a motorbike? And then if you get permission, you open the gate and you go to the other side and open the gate and you get in your car and you drive it across and you close it and so on. And quite often these days, that's where the level crossing accidents happen, because people don't bother to phone the signaller, or they phone the signaller and the signaller gets it wrong as to where the train is. Because although you've got track circuits, you can have quite long track circuit sections. So you know the train is somewhere between here and here, and your crossing there. You need to know whether the train is there or there. And you don't necessarily know that from your system. And sometimes you get harvest time, for example, because lots of the farm tracks. At harvest time, the signaller can get 50 calls in a day asking to cross these little farm tracks. So that's actually been something that the accident investigation body, the Rail Accident Investigation Branch, have been really looking into recently, yes, where a lot of accidents have been happening. I think I've pretty much finished all those anyway, and you said that was the last one, so I think I'll stop there.
Thank you very much, Robin.
Get myself back on the screen. There we are.
Thank you again for a really fascinating and engaging talk. As you can tell from the large pile of questions, and I'm sure we could have had quite a few more, and unfortunately we didn't get to a couple on YouTube. Yeah, thank you again very much for that. We have a round of applause for Robert. We will be back on Monday the 5th of September talking about nuclear fusion and the path to net zero electricity. And hopefully we may have learned from a few accidents with the technology by then. Thank you all very much. Goodbye.